Hello everyone, this is the solution to homework 2. Now, the question was to implement a matrix system, sort of, that uses a static memory. And it had some functions to implement. For example, if we push, for example, a matrix, we will use mat push. It would add a certain matrix with a provided data that is in data, and it has a m by n size. It would be added to the static memory. Of course, then the mat count variable here would be incremented. We had some capacity here. We have to check if the capacity is not full, then we push an element. And the size len here is the maximum size that we are talking about. And when we pop a matrix, we will to remove a matrix from the memory. We were able to add matrices and subtract matrices so that it would pop the last two matrices, add them or subtract them, and then push the result back in. And we had some mat dump here, which would show us all the matrices available to us in the memory. And we have a mem dump for even deeper inspection of our memory, so it would just give us the whole memory. It was just print out the memory. We had templates here, which I'm also going to use. We had a main.c file. I just downloaded it here and placed it here. And I have also the student.c file, and of course a compile file, which compiles both of them and generates our main file here. I didn't touch anything. I'm just going to fill in these parts here, and that is going to be it, basically. Now, the console output is given here. I'm going to come back to this here, but let's first dive into the most easy function here, which would be the memdump here. So, when I use the template, I'm just using the template. I'm just downloading it. I'm just going to compile it here like this. And when I run it, like main, I will get memdump because I've just written one line of code here, printf memdump, and that is going to be it here. So now we have already the definition of our static memory here, and we're going to use that. So let's actually dive into it. Now, first of all, let me just indicate that we're talking about the memory here. Memory, new line. I'm sorry, and that's it. Now, we are going to basically just printf it because we have a float memory. We will use printf, and I guess I did say it, but let me check again. I don't remember showing it. But in order to save space, let's just restrict the digits here to 3. So 0.3f would be a good choice here. 0.3f should be a good choice. Of course, the space to separate the elements. And then what I'm going to do is I'm going to just print fmem_i, because these are the elements that are going to be available here. And when we're done, we're going to have a new line here. Not really important. Now, since I have a certain memory, I need to just print out the whole memory. I don't even look at the capacity or anything. I'm just directly going to plot the whole array here. So what is the size of the array here? Well, basically it is going to be this one here. The whole thing given here is basically the size of our vector. Therefore, I'm going to place in a4, place it in here, and once we're done, we're going to have that. Int I starts from 0, I less than this whole, oh, let me just copy it back. Yeah, it calculates it even. Having VS Code as assistance is sometimes very nice because it shows you that it makes 12 at this point. Yeah, it's quite nice to know that. And then I++ And I guess we are good to go here. And by the way, let me explain what this whole mess is. We have mat size len, which is the maximum the row or column capacity. In this case, we have 2. Since we will have a 2D matrix, it means that at most we can define a 2 by 2 matrix. It could be 1 by 1 scalar, it could be 2 by 1 vector, 1 by 2 vector, or a 2 by 2 vector. Therefore, the maximum size that we can occupy here is 2 times 2, which makes 4. So 4 floats would be the content of one matrix. And then we would also store a float number for the size data here for row and column, so 2 float numbers for m and n. So therefore we will have basically 6 of that. And this whole thing here is multiplied with the capacity, which means that this many matrices can be held in the memory. So that's also times 2, which should end up being 12. This is basically 12, so we start from 0 to 12. We're just printfing whatever we have in there. So in Windows, I'm not sure if it's also in Unix systems. It should also be working in Unix systems. If you apply this and operator here, it means that first run cls and then compile.bat and then main.exe. And that's basically our memory here. The only thing that I've just printed out is the whole thing here. You might argue that we didn't push anything, we didn't pull anything, we didn't do anything at this point because mem dump is actually called here. I didn't touch that, but it did work because mat push doesn't do anything. Mat push doesn't do anything because they're not implemented yet. Mat subtract and dump do also nothing, but I implemented mem dump, therefore this worked right out the box and we just saw the result here. So basically, all that I wanted to do is just printf the whole float mem memory that is defined by this line here. So mem dump is just dumping the whole thing. So what if we want to dump the matrices? So this dumping here is quite a technical term, and well, it's just showing whatever it is, or just placing it on the screen. So it's dumping it on the screen. Now here, memdump is just raw data in terms of memory, but matdump is a styled data where we will have matrices. As you can see in the PDF here, down here, the output gives us an indication that there's, for example, just one matrix here, and it would look like 1, 0, -1, -2. And that's basically it. Now, therefore, we will be writing a code that will printf matrix by matrix. So let me just start with printf here. Let's call this matrix and then maybe which matrix it is. But I'm going to go into detail later. So let's just place in a new line. Now, the first question here is to ask ourselves is to what is the size of our matrix and where is that data hidden? Now, at this point, when I call matdump at any time, it will look at the current state, at the current value of mat count, at the current value of mat cap and mat size len, and it will determine the sizes and printf everything. So it should be based on the mat counts here, and it should use these define statements here in order to generate the output. Because at any time I will call this, and it should give me the screenshot sort of that time instant where it is called, and show me the matrices that are available there. Because I will use this for debug purposes most of the time. So therefore I need to find out what m is, and what n is. By the way, since we're using float data, we're actually losing some memory here, but it's not really important because we cannot have floating point numbers for sizes. So it's a decision, but since we're using a block of memory, we're okay with that. So yeah, not important. And the capacity will have a reasonable limit, so we're not concerned with that. So how can I find this m and n? Well, I will use the mem here, the memory here for both of them. And well, the thing that I should look at is basically this multiplication here. It's so, well, basically, if you look at the PDF, let me try to explain it from there. If you look at the PDF, you will see that there's a matrix 1, 2, 3, 4, and the last two ones are basically the sizes here. So what I'm trying to do is the same, but I need to access the corresponding sizes here. So if I place these two, one issue is that which matrix am I looking at? And I might solve that by just multiplying this with 1. Let's say we're looking at the first one. So if I'm looking at this memory address, it would be basically the beginning of the next matrix here, if you know what I mean. It is a bit interesting, so let me just calculate this. So this is 2 times 2. So basically the inner of this parenthesis is basically 6. 2 times 2 plus 2 makes 6. So this would mean that I'm looking at mem 6. But if I have just one matrix, 2 by 2, plus 2, it would mean that I would look for the interval between 0 and 6. So there should be 6 elements, but 0, 1, 2, 3, 4, and 5 makes up 6 elements here. So I have already 6 elements here. This would mean that the next matrix would start at 6, 7. So the next matrix would start at 6, 7, 8, 9, 10, and 11. And then it would start with 12, 13, 14, 15, 16, and 17. And if it's 18, it would be the new line. So basically, this is because we have metcap 2 and metsize len 2. So 2 by 2. So if this is n, it should be n squared times matrix capacity. In this case, everything is 2, so it gives me the number 6. And if I'm talking about 1 times this, that would be basically 6 here. So I'm starting with the first element of the next matrix. But I don't want that. I want to come just 1 or 2 places back because I'm interested in 4 and 5. So since the last one here, if I subtract -1, it should come 1 back here. So this is the whole data here. This is data. This is m, and this is n. So therefore, this would be n because I'm coming 1 back. And if I subtract 1 more, it should give me the m value and n value here, if I'm interested in the first one. So this is basically going to be iterated here, because I will look at met count. If it's 0, I cannot print anything. If it's 1, then this should be, for example, the size of the first matrix here. Now, from this point on, I'm going to have a for loop here. It would be int I equals 0, I is less than m, I plus plus, all that classical for looping thing. Now, let's look at j, because row column, so n, j, j, of course j. So, now, We again are going to printf something here, maybe printf percentage %f. We could place 0.3f, but since it's just a matrix, not really important. And again, we're going to access something here, so mem. But now we have a little bit of a problem because we are using a 1D memory here, and we are using a 2D structure. So it means that we are basically using 1D array to store 2D arrays. And the way that we accomplish that is by basically, so let me just leave it there. If we have, for example, 1, 2, 3, 4 as the matrix data, what we do is we say that the first two elements are the first row, the next two elements are the next row, so all the rows will be side by side. Instead of having something like, instead of defining a matrix like this, since this is 2D data, what we do is we just combine all the rows with each other in one line and store it like this. So it makes then sense if we have a static memory and a n by n part to hold the whole data here. Because then we try to access each row and column so that it seems like a matrix but is actually a vector in real life. So instead of having a n by n matrix, we actually have a 1 by n squared vector. We stored it like this in memory. It has its advantages. We can define 2D stuff in C, but we are going to stick with 1D because it has some performance benefits. So, well, apart from all this thing, since we have multiple matrices in here, apart from all the offset and stuff, let's focus on the first matrix and how we can access the data here. So M is basically the number of rows. So this is rows. And this is basically columns here. And I'm just trying to print or access the columns here. And if I go forward, I should actually use J. So J is a nice thing to have here, and I'm going to add J to stuff. I'm going to have an offset, so let me write down offset, but I'm going to increment as I increment the column because it is basically printed column wise, but stored with multiple rows. The problem here is to access the right row actually. So I need to, by the way, we have the column size here, n, which means that how much data in a row is whole here. So if n is equal to 2, for example, I mean that I'm separating them by 2 and try to access them like that. So therefore, I need to multiply 2 times the I here, the row here, in order to have the offset that corresponds to that row. For example, I starts at 0. So if I is 0, let me add j to this. So this is basically going to be the formula that I'm going to use. If I is equal to 0, it would be the first row. So I would start from the beginning, from 0. And if j is 0, this one would be the element that I'm accessing here. If j is equal to 1, this would be the element, and we're good to go. If I'm interested in the next row, I would be incremented to 1, and it would look like 2 plus j. So what I'm really doing is I'm using 0 plus j, 2 plus j, and 4 plus j, maybe 6 plus j, but j can only be 0 or 1 because it is less than 2. So it would then categorize, or it would then access the according row data. And if I use printf new line, I would just generate this matrix here that looks like a matrix, but is just a 1D vector here, like this. So therefore, our general formula for this type of axis is basically j times n, j plus j plus I times n, or n times I. So let's use that. So now if the offset is 0, we have no problem. But if we have another offset, then this would become a little bit of an issue here. But we have a solution to that, because accidentally I found out that if I use this thing here, that's actually my offset. Because because if I use this starts with 6. Of course, I might need to multiply it with 0 to access the first one, but this is the whole thing here is 6, computes the 6, and if this is 1, for example, it will jump 6 elements, and I will end up in the 6th element, which is the first memory of our next matrix, as you can see here. So the indices 0 up to 5 belong to matrix 1, but from 6 to 11 they belong to matrix 2, from 12 to 17 they belong to matrix 3, etc., etc. And it is basically a power of 6, a multiplication of 6, and I can associate this 6 times something as an offset, so I can offset myself to the right matrix here. Now, well, if we have this offset here, we can just print it out like this. Let me just get rid of that. Let me put in that. And since this for loop here prints column-wise, I will add a printf new line at the end of the column, so I will generate a new row. And once we have done that, what we can do is maybe we can just add another space here to have extra space. Yeah. Now, let me just get rid of this whole thing here, but let me comment this out. Of course, the issue is that we have multiple matrices. Now, just plotting, printing one matrix is problematic enough, but we have multiple of them. So let me see. Seems to be okay. Let's actually try this out. Let me just compile and run it again. Now we're trying to access something, but since everything is 0 here, we didn't put anything into that, we have kind of an issue here. But I can get around with it when I just go ahead and do something. Let's actually, I am not supposed to do this, but let's come here. When I call memdump, I'm just going to assign certain values here. So 1, 2, 3, 4. So 5 and 6, as you can see here. 5, wait a minute. This is the data. 4 and 5 should correspond to the sizes here. So let me just change them to 2 by 2. And also 10 and 11 should be, I guess, the 10, 11. They should also be the sizes of the next matrix. So let me run it back again. Voila, there we go. Now you can see I just manually injected some data into the memory, and I can see that there are 4 entries of zeros, and we have the size 2 by 2. And then again 4 entries of zeros, and again the size of 2 by 2. And you can see that the first one here is basically 0. Therefore, let's see, I0, J0. So 0 times 2 plus 0, it's essentially 0, and this whole thing is 0, so we're printing f the first one here. J is incremented by 1, so we have index 1 here. You can place a printf here in order to see which index is generated, but I can also tell you what it is. And then, since n is 2, j is 1, we're done with this for loop. We go a new line, and then we start from I equals 1. If I is equal to 1, we can see that 2 plus j is now the formula here. J is 0, so 2, so mem2 is printed, and then mem3 is printed, and then we're done with the for loop, printf new line, and out of the loop we are. So, actually, what we need to do now is to write our for loop so that we are basically looping throughout the matrix capacity. So I'm going to manually also set the value of this to 2 because I'm going to rely on it here. So again, we need a for loop here. And this for loop would be then int, let's call it k equals 0. K is less than the matrix count. And then k plus plus, and there we go. So this is going to be the percentage d matrix number this, and since k starts with 0, if I place 0, we would be counting from 0, so it doesn't make sense. So let's use k plus 1. And actually, since I have 1 here, if I'm looking for the first one, the offset should start with 0 times this. So basically, since k on its own is 0, I can just place in k plus 1 instead of 1. And we had a 0 here. You can place k instead of this one here. And yeah, this should actually be it if I'm not mistaken. And the reason behind that is the following. If k is equal to 0, this would be 1, and 1 times this would give us 6. 6 minus 2 would give us 4. We would end up in this spot here. And minus 1, which is just one more, would end up in this spot. We're extracting the data from behind. Whereas here, we're accessing the whole thing from the front, from the beginning. So therefore, here we have k plus 1. Go to the next matrix, come back 2 spots and 1 spot in order to find out what this is. This is not the only way. You can also work your way out from the other part. You could just use this plus something that will give us m and n, but I'd like to do it like this. Yeah, it depends on your implementation. But there are multiple ways, of course, and this is the way that I ended up using here. Now, here we again start with 0 if it's our first matrix here. And if it's 0, there's no offset, just use the data. If k is equal to 1, add 6 to it in this case, but keep in mind that I'm using mat size len here and the mat capacity stuff here, etc. I'm using these definitions here so that I don't, so that it will update itself for different values, and we'll experiment with that at the end. So let me compile. There we go. If the memory looks like this, I injected this data here somewhere. I'm going to erase this when I implement push, basically. But here we go. We have matrix 1. It looks like this. Matrix 2 looks like this. If you want to have fun a little bit more, you can check if it's working by just placing an arbitrary number here and compiling and running it back again. You can see it appears on the right spot. If I change it to, let's say, 3, it should be on the next row, first column. If I'm not mistaken, yeah, there we go. So 0, 1, 2, 3 is the last one. 4 would be the data here, so 3 is the last one here. 4 and 5 would be the size data here, etc., etc. So it seems like we have resolved our problem here in terms of mat dump. It seems to be working now. Now let's get rid of this whole thing here, this whole injection stuff here. And let's compile and run it. And we have no output whatsoever. Because the memory is empty, the mat count is 0. If that's 0, this for loop does not work because 0 is not less than 0. So we skip this whole thing and it is fine. The memory will dump always because it's just a raw method here. So what about mat push? Now you can see that we have created a matrix here and we are trying to push that. The first two ones are about size and the next one is basically just the matrix address, or the matrix, the vector here that we've created here. Now here we have the size data here. We have the data itself in a pointer. The only thing that we need to do, or we should start with checking if the capacity is not full, because if it is, we are just going to show a message. So else, let's printf capacity full, new line. So how can we check if the capacity is full? Well, we have this mat count here and a mat cap. So as long as the matrix count is less than matrix capacity, the definition that we had, we're good to go. We have still one left because at worst case scenario, that this would be mat cap -1, and if we add 1, it would be exactly equal to mat cap, and we would be stopping at that point. Now, of course, since this time it would be an assignment here, what I'm going to do is I'm just going to copy this for loop here, like this, because I'm going to access the memory as like always the same. So this would be the accessing of the memory here. Yeah, let's see. The issue here now is to calculate which matrix we are inserting in. And basically, K here is the offset that we don't have at this point, but we know how many matrices we have in the memory. So this is going to be incremented when we push a new matrix into the memory. So therefore, if for example we have mat count 0, at this point we will be adding at 0. If this is 1, we would be adding at 1. So the offset here is actually mat count itself because it starts with 0, and in this case, if you look at the memory, we have nothing in the memory, and therefore the offset should be 0 here. So the mat count itself can help us in determining if we should add at 0, at 6, at 12, at 18, etc., etc. So if the count is 0, which is possible, then we're going to use the 0 offset. If we have already mat count equals 1, which means that we have a matrix in our memory, it would mean that we should start with the next index, or the offset should be equal to 6. And the number 6 is basically calculated from this here, but we're multiplying with a mat count, so we end up in the right offset here. And other than that, we actually have the exact place of our data here. The only difference is that we have a vector here, or an array, in our main function, and we want to copy the content of that. Since this is basically data here, we want to copy the entries of this. And I'm not going to mess up the ordering. I'm not going to mess up anything because I'm going to copy it as it is. But the only difference here is that here mem is a global memory, a fixed static global memory, but data here is a local memory. So the only thing is that once we have this global offset here, the indexing here, or the 0th, the 1st, the 2nd elements should go along with that. So n times I plus j here generates actually 0, 1, 2, and 3 in our case, and nothing else. So we will have a global offset here. It could be 6 times 1, for example. Then the global index here would be 6, 7, 8, 9. So it would mean that 6, 7, 8, and 9. So I would copying 0th element of data to the 6th element of our memory. And the first element here to 7, the second element to 8, the third element to 9. So therefore, I'm just erasing the whole offset thing here. But other than that, I would access the local data memory here using n times I plus j, because that's basically the movement of the matrix elements. But here we will just have a offset. So once we have done that, we have actually copied the whole data, but we didn't notify our mat count here. So once the for loop is over, we can increment the mat count because we have added one matrix to the memory. But still, we have to add something more, and that was extracted in here. I'm just going to copy this here. There we go. We have to set these to m and n because we have to store the size data here. But as you can see, since this was mat count and we were starting from the left, actually, we start from the top of the vector or the memory here, but here we are using basically the last element. We go back, so we have to increment this. So if this would be k here, which is basically also k here, this is k. If that's k and that's k plus 1, it would mean that mat count plus 1 would do the job here, because it goes to the next matrix, comes back 2 elements, sets it equal to m. It goes to the next matrix, but comes one back and sets that to n. Now, actually, when we run this, what we should see is, since push is called twice, without tinkering with anything in memdump here or matdump here, we should see that there should be 2 matrices in our memory as we should expect it. But it seems like we might have a little bug in here because, well, since we're incrementing this, this might be an issue. Maybe changing the order here would help us out. Exactly. If you increment it and then use it like this, let me bring it to the original. Here, mat count was 0. We incremented, it is equal to 1, and then I'm adding one more. It doesn't really make sense. You could move this to the to this spot here so that it uses the incremented value, but then it doesn't make sense. If we are going to do this, we might just use it like mat count. Since it is incremented, we will use the incremented value here so we don't mess up anything. So we compiled it, we see 2, 2, 2, 2, and 1, 2, 3, 4 are in memory, and that was our intent because 2, 2, 2, 2, and 1, 2, 3, 4 are in memory. So this was basically mat push. I didn't do anything to the data, I just pushed the data here. And yeah, when we try to do it another time, what would be the result here? Yeah, we have memory. So let me just call main here. Yeah, we can see here it added everything to the memory, but it couldn't add the last element here, where it said that the capacity is full. It added the two elements that it wanted to add, and it worked like it should work. Now, well, we have memdump, we have matdump here somewhere. There we go. So it works accordingly. We can see that data is stored here. There's some size data here, and then 1, 2, 3, 4, and then again 2, 2. You might want to. I didn't decide or opt for it, but we could have done some fancy things about the sizes here. Maybe in a parentheses, comma, separation like that. So we would see which one is data, which one is what. But yeah, I didn't bother to do that. So now, once we have done that, we also have the pop operation, which will get rid of stuff that is already available in our memory. So now this is actually quite easy, because what we have to do at this point is go to the last matrix, set everything equal to 0, and decrement the mat count variable, and that would be it. So therefore, let's first of all we have to check if there's something to remove, and we can just printf memory empty if there's nothing to remove here. But other than that, we can decide based upon mat count if it's a positive value. Because if it's equal to 0, it is empty. But if it's a positive value, it means that at a worst case scenario, we would have 1. So if there's just one element, we can remove that. Therefore, we are going to go into this if block here. So I'm going to have a for loop here. All that I'm going to try to do is do this. And once we're done with that, mat count should be decremented, and we should be good to go. The only thing left here is to decide upon the details of this for loop. So, int I equals 0, I is less than this value here. I could have actually used also a local variable for this, but yeah, not going to do it. I plus plus, that should be equal to 0. Now, the only thing that we have to do is look basically at the global offset, because something plus I would be the result here. And why is it something plus I? Because I will be incremented from starting from 0 up to 6, basically. Does it show me? Come on. Nah. Yeah, it doesn't calculate it like I wanted to do. I wanted to see, but I know that it is 6, so it's from 0 up to 6, so it will basically cycle through 0, 1, 2, 3, 4, 5. So it should add something to this, because it has a global offset here. Now, what is the global offset? Well, the global offset is also calculated using this here. If you remember, we have this mat count thing here. Let me just take that. So it's basically mat count this plus the offset here. So I'm going to use the same thing here, mat count plus that. But the problem here is if we are using mat count, and if mat count is equal to 1, it would be 6 plus I. So we would be looking at 6, 7, 8, 9, and then, yeah, whatever. But we don't really want to do that. We want to subtract 1 from mat count, because then we would start from 0 here if mat count is equal to 1. So here we are referencing basically the previous matrix. If there's no such thing, this would be equal to 0. Now plug in 2, for example, here. Then we would start at 6, 7, 8, 9, 10, 11, as it should be. If it's 1, we would start at 0, 1, 2, 3, 4, and 5. So this is basically the intent here, and that should basically do it here. Now let's come to here. Let's not dump that, or let's dump that. Don't subtract it. Let's just pop 2 matrices and then dump, or maybe just pop 1. Yeah, what did we mess up here? Let's see. Oh, I invented a new function name. It's okay. There we go. Now we can see actually the memory dump was the original dump. If we look at the main function here, we pushed 2 functions, we dumped the memory, but then we popped 1 and then we dumped the matrix memory. So what we can do is we can maybe just repeat this mem dump here in order to see what's going on. The memory looked like this, then we did just erase everything here so that we have just one matrix here. So we can conclude that pop actually works here. I guess this was the original one here. So now what about matrix addition? And then, as a matter of fact, also maybe subtraction here. So if we want to add matrices, we have to do a similar check here. Let's place it in here. But this time, the check will be a little bit different. The reason for that is the following. If we have mat count positive, it means that we will just have one matrix. But if it's greater than 1, it would mean that we would have at least 2 matrices. This is the important thing about this, because we need at least 2 matrices in order to be able to add them together and then place them back to the memory. So else we are missing an operand. So there's just one element missing here. So how can we add stuff or add matrices? Well, there are several ways to accomplish this, but I'm going to go again with a lazy one. That is that I can reference the memory itself. Just don't mess up the ordering. For example, here, I know that the sizes are these. Here, for example, 2 by 2 and 2 by 2. I would just directly add stuff to the memory here. So I have one offset, or the data lies here, and then I need to skip that. The next data lies here. I would just go ahead and take this part, add it to this cell, take this part, add it to the according cell, repeat it one up to the end, and then just pop the last matrix, and the size is compatible, etc., etc. So this is a lazy way of doing it, but you can maybe attack it more professionally. But yeah, if it works, it works. If it works for all scenarios, why not? So I'm basically taking this approach, and there's no matrix multiplication. It could have been added to this system. Of course, it would make much more sense, but then it would be too difficult. That's the reason why we don't have multiplication. We have addition and subtraction, and that's basically it. Now, well, I need to go. So basically, from the pop operation, I know that this is one previous. So if I use -2, it would be the first matrix that I'm talking about here. So basically, this plus I plus equals this one here should do the job. That's what I'm trying to tell here. So I'm basically referencing this one here, but I'm not adding 2 here. So this is now 4. Now this is the length of the data here. So that's data length here, 4 in our case. And I'm referencing the first one here. And if this is, at least this is 2. I know that, because otherwise I'm not entering this if. So if it's 2, this becomes 0 offset. So this vanishes here completely. Then I'm referencing the ith element, which will be going from 0 up to 3. But the next row would be adding 6 to it, because this here computes to 6. So I would be using 6, 7, 8, and 9 to compute this. So I'm adding the 6 elements of the static memory to the 0th element. I'm adding the 7th element to the first element, the 8th to the 2, the 2nd, the 9th to the 3rd, and that's basically it. Of course, I need to check the size of this. If both are equal to each other, then I'm going to do it. If not, it's not. So, of course, that's necessary. I'm going to add that in a moment. But you can see that this is basically a direct addition or subtraction method here. And once I'm done with that, I'm assuming that the sizes are compatible. I have all the data necessary here in the first 6 elements here, and I have computed the actual data here. So I don't need to do anything about the sizes or anything else. Therefore, I'm just going to matpop. I'm going to remove the last one here because I don't need this data here anymore. The result will be the same size, and the data will be updated manually, and that should be basically it. So let me just do it like this. And yeah, there we go. Now let's first try to do it. There we go. Let's come back here. Let's try the addition. So this is the memory. We had 2, 2, 2, 2, 1, 2, 3, 4. So you can see 3, 4, 5, 6 is the result here. And we have just removed that. I can show you that basically like this. You can see I've just erased the whole thing using matpop, but I didn't touch 2 and 2. I just added the necessary data from here to there, from here to there, like that. So let's get rid of that. This should be the original version here. There we go. Now, yeah, it is quite easy to check if the sizes are compatible. So, well, yeah, we can do it. If now we could just use basically this one here. Now, if we do this mat count that minus 2, that would be m. If this is equal to mat count times that minus 2, and the other condition, of course, it's becoming too long at this point. So this and this, where I'm extracting just 1. If these are equal, I'm going to do that. Else printf size mismatch new line. So let's compile. There we go. Let's try addition again. There we go. Still works. Now, of course, we could demonstrate if it's not equal to each other. We could just mess up the sizes here, I guess. Hope that I didn't mess up anything. Size mismatch. And yeah, it still works. You can see that it still works. I couldn't add them together. For some reason, I added a 2x2 and a 2x1 matrix. Size mismatch, and we're good to go. Now, of course, since we're at it, I can just go ahead and completely copy this and add it to here, and just change the operation here to minus equal, and this is basically the only difference here. Yeah. Let's change it back to subtraction. Let's compile it and run it. Size mismatch. If I don't mess up the size here, then we get basically to the output of the PDF. So that's basically it here. So let me quickly recap. We have the matrix capacity, matrix size length definitions here. Here we calculate the maximum amount of domain or area that is needed, or memory that is needed for just one matrix. And it could be a square matrix, and the limitation is mat size len, so n squared plus 2 for m by n. We are storing the sizes in the memory too. So this makes, for this case where the definitions are equal to 2, this makes 6 times 2, so we have 12 float numbers here. So, and by printing, we just go ahead and cycle through each float number and show them to the screen. But if we use matdump, which is going to produce matrices on the screen or on the console, what we do is we cycle through the matrices that we have at hand, and for using a for loop, we access the end of the memory, go back 2 times to get the size of m, or the number of rows, the number of columns. We use then a nested for loop to print f the matrix data here. The important thing here is that the structure that we use to hold the data here is n times I plus j, because n is the column width, so it means that in one row we have n elements in the column, so that's going to be our offset. For I is our row, so n times I computes our offset. J is just a column offset, which is linear, so we just use that, and we use k times here because that would be the corresponding offset to our matrix. Once we've done that, we have a matrix push, which is basically the same, which does the same, checks for the matrix count to be less than the mat cap definition here. We have a local offset here, which is the same for both because we're copying one by one, but we have a global offset for the left one because we have a global memory. We increment the matrix mat count, which is responsible for the count of matrices, but then we need to be careful because since that's incremented, we are already at the new matrix position. We go 2 back and store m and store n. If the capacity is full, we display this here. The pop operation is quite easy if you can handle the offset stuff here. Other than that, we're just deleting, or we are decrementing the mat counts counter here. But other than that, we just go 1 back, erase the data, erase the size data, and just move on with our lives. In the matrix addition, we just need to basically check if the sizes are compatible. Therefore, we have to check for example, 4 and 5 and 10 and 11, I guess. If they're equal to each other, then we can just do the stuff here. Of course, this is going to the next one, come back to. This is going to the previous one, come back to. Therefore, it is basically the first and the second matrix that are going to be added if we are left with only two matrices here. And once that's checked here, if this checks out, we just go ahead and use the data, access the data, just add them together. Of course, if this would have been a matrix multiplication, then this would be even more complicated, but at this point, we didn't want to overcomplicate the homework because it might be difficult already. So we pop the last matrix here. You could just store the data of the first one, the second one, pop both of them, create a new addition, push that back, etc., etc. But I feel like this is more optimal because it directly references the addresses. It doesn't create extra memory. So the addition is carried out with this. We're adding the to be deleted matrix contents to the previous one, and we're getting rid of the job here. And this is basically the same with a minus sign. So you can experiment with stuff here. We could, for example, define a 9 by 9 matrix, push them 3 by 3, and instead of memdump, which is not really that important at this point, just mat dump it in order to see if it's working or not. So let me just 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 0, 0, 0, 1, 0, and maybe 0, 0, and 1. So let's try that out. You can see we have 3 by 3 matrices. We can then maybe add them and dump them back. So we have this neat little system where we can add matrices. We need to clear this, call main. There we go. Matrix 1 was this, matrix 2 was this. We add them together and we deleted stuff. So this is basically our result here. But of course, since the matrix capacity stuff is not incremented, we have a little issue. I have to go to student.c and increment the maximum size because it still works, but it shouldn't actually. Let's compile it. Let's erase it back again. Let's run it. Now we see the whole result here. We were out of memory, by the way, and we didn't actually say that we are out of memory. We can just develop the system to detect if we are plugging in something that is greater than it fits, and it's also actually quite easy to do that if you go to mat push here. Here I didn't check if this M and N is basically so if M is less than the capacity and N is less than or equal to the capacity, so basically by capacity I mean mat size LAN, we should immediately add this here. If this is less than or equal to that, and if N is less than or equal to that, so that if someone wants to push something that is greater, it should not do it and say the capacity is full. So let's compile it. Let's run main. Capacity full, missing operand. So at this point, we prevented this from being happening. Now, if we increment the len here, it should be good to go. There we go. Now we can see it's working now. Now, as I've talked about this, you could just go ahead and maybe develop it further. You can add the matrix multiplication, matrix inversion, and stuff like that. And you could even go a step further to try to calculate some optimization problems, etc. Then you have this neat little thing that uses memory efficiently. This is memory efficient because we have a stack memory. because it is a static memory. We're not allocating or deallocating memory. We're just wiping out the data, or we're just using the data. By the way, for the matrix pop function here, if we have speed optimization, if we want to be a bit more faster for these calculations, we could just skip this here, just decrement mat count, don't even wipe out the data, just leave it as it is and just move on with our lives. So that's also possible. We could optimize stuff a little bit further, but I hope that you had fun with this, and I hope that you could have coded the majority of this homework. So, see you in the next videos.